Good day, students. Welcome to the AP Calculus AP exam review. We're going to be going over problem 1 on the free response question for 2006. And this problem addresses concepts such as the area between curves, volume of solids of revolution, and volumes of solids with known cross-sectional areas. So before we get started, let's take a look at some formulas that are going to be guiding our problem solving process. So title it formulas. All right, first one has to do with area. So the area formula is basically the integral from a to b of the function on the top, let's call it f, minus the function on the bottom, let's call it g. It could be the function to the right or the function to the left. All right. How do we know the orientation? Well, dx basically indicates a top-down orientation. Function on the top minus the function on the bottom. In this case, the slice, the cross-sectional area of the rectangular region is going to be perpendicular to the x-axis. Or dy is a situation where you're looking at a function to the right minus a function to the left. Okay, in that case, your rectangular region will be pointing to the y-axis. Okay, with this orientation, g is less than f. Okay, either g is to the bottom of f or g is to the left of f. Now, volume is a little bit more intricate. Let's take a look at the formula for volume. So volume is the integral from is pi times the integral from a to b of the outer radius, big R square, minus the inner radius r square. Okay, that gives us the area of the washer, and then when we integrate from a to b, we can find the volume. Dx is when your radius is perpendicular to the x-axis or pointing to the x-axis, and then the y is when your radius is perpendicular or points to the y-axis. Now there are two scenarios here, depending on the orientation of your axis of rotation. So let's take a look at the two cases. The first one, pi times the integral from a to b. If you're looking at a top-down orientation where top-down or left-right, if the axis of rotation is less than the two functions, we're going to have the function on the top or to the right minus your axis of rotation square. This is big R square. Pi R square will help you find the area of the bigger disk, minus g minus a square. This is little r square. So pi times that square will give you the area of the inner disk, and then when you subtract these two areas, you get the area of the washer. Okay, so dx, if your radius is perpendicular to the x-axis, or dy, if your radius is perpendicular to the y-axis. All right. So this situation is applicable when a is smaller than both functions. Either it's at the bottom of g and f, or it's to the left of g and f. Okay? And then the other situation we have is pi times the integral from a to b of a minus f. This is big R. The difference here is a is bigger than both of the two functions. Okay, so a minus f square will give you the outer radius, minus a minus g square will give you the inner radius. Dx, if your slice is perpendicular to the x-axis, or your radius is perpendicular to the x-axis, or dy, if your slice is perpendicular to the y-axis. This orientation is applicable when f is less than g and g is less than a. It's like a reversal of the order here. Okay, I always like to put f at the end and then put g in the middle and then a at the other end. So this formula is applicable to revolution, solids generated as a result of revolution. Now, how about the volume of solids with known cross-sectional area? That's very straightforward. That one, the volume is simply going to be the integral from a to b of the cross-sectional area. Cross-sectional area. It could be A of x or A of y, depending. So it's dx if the base is perpendicular to the x-axis, or dy if the base of the area is perpendicular to the y-axis. So this is for cross-sectional area. Let's put that note there, cross-section. The only hard part with this last formula is finding the area of the cross-sectional area, because you have to make use of your geometry formulas to find the area. Okay. All right, let's take a look at problem 1. The A part says let R be the shaded region bounded by the graph of y equals ln x and the line y equals x minus 2, as shown above. Find the area of R. Okay, so to find the area, it's good to use the formulas to guide our problem solving process. So the formula for area that we talked about earlier is the integral from a to b of f, the function on the top or to the right, minus g, the function at the bottom or to the left, dx or dy. Now here we have a situation where regardless of how we cut it, our region, we're going to have one function constantly on top and one function constantly on the bottom, or one function constantly to the left and one function constantly to the right. So this one, since the problem is already in terms of x, we might as well slice in the x direction. Okay, so we're going to be going top down. That's what our slicing is going to be. So let's go ahead and put in the intersection. You can use your calculator to do this. Hopefully you know how to find the points of intersection using your calculator. If you don't, I have a lot of tutorials that go over that in detail. So you just find the points of intersection using your calculator. We have 3.14619 and 1.14619. And then for this point, we have 0.15859 and negative 1.84141. So those are the coordinates of our points of intersection. Now, since we're going top down, we're going to be working with just x's, okay? So this will be, we're going to be focusing on our limits of integration will be, this will be a, where we're starting from, and this will be b, where we're ending at, okay? So this is x and this is y. Now to apply this formula to this situation, we're going to first of all put in our limits of integration. So we're integrating from, the lower limit is the smaller x value, 0.15859, and the upper limit is 3.14619 times, now f, remember for this formula, g is less than f. Either g is to the left of f or is beneath f. Since we chose to slice in this direction, like this, what's on top, what's on the bottom? F is on the top and g is on the bottom. Okay, so let's label our functions too so we know which is which. This function that's curved right here, this is our logarithmic function, ln x. And then this function down here is going to be our linear function, x minus 2. So if we apply the formula to this situation, the function on top is a logarithmic function. So ln x minus the function on the bottom is the linear function, x minus 2. And I have to be careful here to put this in parentheses, so you have a error with the sign. And then that dx, that will give you the area. All right. So let me should give you a visualization as to what's going on here. All right. So you have the two functions, the logarithmic function in blue and the linear function in brown. So what we're doing is we're basically adding up all these infinitely narrow rectangles from our lower bound all the way to our upper bound. That's how we calculate the area. Okay, it's like an accumulation of all those, the area of all those rectangles. So let's take a look at what the area is. So you're going from 0.15859 all the way to 3.14619. Okay, so that's net accumulation of those areas is 1.949 square units. Okay, all right, let's take a look at the B part. So for the B part, it says find the volume of the solid generated when R is rotated about the horizontal line y equals -3. So we want to orient our functions relative to where the axis of rotation is. Y equals -3. We know that it is clearly below both of these two functions. It's somewhere down here, okay? So since it's beneath both functions, we're going to be using this formula right here. So always let the formulas guide you. They're really helpful. We're going to be using V equals pi times the integral from A to B of F minus A squared minus G minus A squared. Now, is it going to be the X or the Y? Notice that we are rotating in the direction of the X-axis, so it's going to be dx. All right, so think about it. We have the two functions like this, and then we have the axis of rotation down here. So we rotate, our radius is basically perpendicular to the x-axis or in the direction of the x-axis. All right, and then you just rotate that way. So this is the formula we're going to use. So f is going to be the function on the top, a is going to be your axis of rotation, g is going to be the function on the bottom. All right, so let's go ahead and write that down. So we're going to have the volume, applying this formula to this situation, is equal to pi times, now since we're using x's, we're going to take the x coordinates of the points of intersection. We already have them here, 0.15859 and 3.14619 times f is the function on the top, and that's the logarithmic function, minus -3. So minus -3, of course, is going to become +3. This right here is your outer radius square, minus g is the function on the bottom, x minus 2, minus a minus -3 becomes +3, quantity square dx. Okay, so this is what you get if you're using the formula directly. Now let me set it up for you by actually using the whole idea of a composite radius. Okay, so let's say we have the functions like this. Well, let me use a straight line. Well, I can sketch this first. So we have the function, the functions intersecting, have the logarithmic function, your linear function, and the axis of rotation. And then what you're going to do is you're going to create your radius, a composite radius. All right, so this right here is your composite radius, and there are 3 points that we're going to extract to set up our formula. Okay, so we have a point on the top, a point in the middle, and a point on the bottom. Okay, so let me put my composite radius here. What I'm doing is basically showing you why this is the case. So there we have, what do we have? We have F on top, this is F, and then we have G, and then we have A. Okay, you notice the order. You can see here that A is less than G and G is less than F. That's why we use this formula. Now this is the radius. What we're looking for is the area of the disc. I'm sorry, of the washer. All right, so how do we do that? What we need to do is we need to take the, we need to find the area of the outer disc, which goes from here, F, all the way down to the axis of rotation, right there. Okay, so that is the first length we have to find. So the question is, how long is this length? From F to G, how long is that? This right here that is our outer radius r, and since we're going top down, it's going to be f minus a. Oh, let's try that again. It's going to be big R is going to be f minus a. So that's why we have f minus a here, but we have to square it, of course, because it's pi r squared. So that's the outer radius. Now for the inner radius, you're going to go from G, let's trace this out, from G all the way down to A, okay? G all the way to A, and that will help you figure out your inner radius. All right, so this is little r, and then little r can be determined by finding G minus A. So that's why we have G minus A squared here. Okay, so when we subtract these two, all you'll be left with is this region right here, and when you rotate it, you have this nice little disc looking something like that. Okay, so that's basically the idea behind this setup. So remember, this is big R squared, and then this is little r squared. Now let me show you a visualization to help you see what the resulting area will be after creating our disk and moving it from within our boundaries of integration. All right, so there goes the function. First thing we're going to do, let me show you what the resulting region will look like. So if we take that area and then area and rotate it around y equals -3, we can see that y equals -3 is clearly beneath the two functions. And then there goes our slice right there, that little washer that we were trying to create. All right, so that's what it looks like. Now to find the volume, we're just going to find the accumulation of all the tiny washers that we found the area of as a result of that formula. So that's where you have the integral from the lower bound of x all the way to 3.14619. And then that will be the volume of the resultant solid, this solid that you see right here. Okay? All right, let's take a look at the last part. All right, so for the C part, it says, write but do not evaluate an integral expression that can be used to find the volume of the solid generated when R is rotated about the y-axis. So what direction are we rotating? Our radius is going to be perpendicular to what axis? Well, we're going to be going in the y direction, in the direction of the y-axis. So what formula are we going to be using? Since we're going in the direction of the y-axis, if you have trouble visualizing it, just think about this. There goes your logarithmic function, your linear function. There goes your y-axis. So we're rotating in the direction of the y-axis, okay? So that means everything is going to be in terms of y. So let's write down the formula. So the formula for the volume is going to be the integral, pi times, let me write this in blue since this is just a formula. The volume is going to be pi times the integral from a to b. This is going to be y's, okay? Y equals a and y equals b of now, is it going to be a minus f or f minus a? That's the question. Now look at the orientation of our functions. This function is on the top. Okay, if we draw a slice, if we slice it, we have that composite radius right here. This function is to the left. This function is in the middle. This function is to the, this is to the right, this is in the middle, and this is on the left. All right, so if we want to label this, call this one F. All right, is to the one to the left, and then call this one G, and then call this A. What do you notice in this orientation? A is smaller than G, and G is smaller than F. So A is to the left of both functions. So if you have this orientation, remember, it's going to be F minus A squared minus G minus A squared, okay? And it's going to be dy. All our functions are going to be in terms of y since we're rotating in the direction of the y-axis. So to set this up, we're going to, let's list everything that we have because of the changes here. Our limits of integration are going to be a equals, we're going to be using the y coordinates now, okay? And then our slices are going to be going from the bottom to the top. So we're just going to be using these y coordinates since we're dealing with the y's now. Okay, so we go from this value to that value. All right, so let's just apply it directly to the formula so we don't waste too much time here. So we have the volume is going to be pi times, now remember we're looking at the y-axis. The lower limit of the coordinates of intersection for the y-axis is negative 1.84141. Get that with a calculator. All the way up to 2.14619. Okay, remember that in this orientation, a is less than g and g is less than f. Okay, so f is going to be the function to the right, and g is going to be the function to the left. Now we remember that this function, the original function right here, we called it f in the original, well, we called it g in the first two parts. So the equation of this linear function is y equals x minus 2. Okay. Now, this function has two forms. If we find the inverse, if we want to express this in terms of y inverse is going to be, just add 2 to both sides, is going to be y plus 2. Okay, so our function in terms of y, f of y, is simply going to be y plus 2. That is expressing this linear function in terms of y. Okay, now the other function, that logarithmic function there, y equals ln x, can be expressed in two forms. If you want to express this using the inverse, you're going to have y inverse equals e to the y. So these two functions are exactly the same thing. These two functions are exactly the same thing. So in the situation of this problem, context of this problem, we're going to have g of y equals e to the y. Okay, the reason why we're putting everything in terms of y is because we're rotating in the direction of the y-axis. Okay, so hopefully you remember how to do inverses from Algebra 2 and Pre-Calc, so I didn't spend too much time doing it here. Hopefully I didn't lose you. So this is the function in terms of y. Okay, so let's plug them in here. So we're going to have the function to the right, remember is left right now, not top bottom. So the function to the right, which is y plus 2, minus your axis of rotation. What is our axis of rotation? Is this vertical line right here, which is basically the line, is a line x, y equals, is x of y. So it's basically x equals 0. So it's the line x of y, f of y equals 0. F of y is the same thing as x. If you think about it, remember y is equal to f of x, and x can be thought of as f of y. All right. So it's x, which is equal to f of y, which is equal to 0. So it's going to be y plus 2 minus 0 square. Let's put this quantity square. This is the outer radius. Think of it as big R square. Okay. And then for the inner radius, we're going to do the inner function, which is the function to the left is the inner function, the logarithmic function. In terms of y, is going to be e to the y minus a. Axis of rotation is f of y, or x equals 0 again. That square dy. For this problem, you're not supposed to evaluate. You're just supposed to set it up. Okay? So this is, you can just leave it like this. So make it look pretty, just drop the zeros. It looks nicer that way. But one thing you want to note is that all your variables have to agree. Okay, you have y, and that's good. So let's write it nicely. This is not necessary, but I just want to make it look pretty. So you have the integral from negative 1.84141 to 2.14619 of y plus 2 quantity square minus e to the y square dy. Okay, if you left it like that, you get full credit. Now let me give you a visualization of what we're dealing with here. All right, so we're using the washes method. So this is basically what the region looks like, rotating about x equals 0. That's what the region looks like. You notice that our radius is perpendicular to the y-axis, okay? Pointing in the direction of the y-axis. That's why all our functions and limits of integration were all y's, okay? And then the resulting solution is going to be something like that. Notice that our limits of integration are the y-coordinates of our points of intersection, and then we have the function to the right, which is a linear function minus 0, like we did earlier, square. That is the outer radius, okay? And then e to the y is the inner function of function to the left, minus our axis of rotation, 0 squared. This is the inner radius, okay? Outer radius squared minus inner radius squared dy. And when you plug it in your calculator, you get 17.099 cubic inches, okay? So that's that. So thanks so much for taking the time to watch this presentation. Please post a comment to let us know what you think about this clip. We appreciate it. And do subscribe for updates to the remainder of the AP Calculus review series. More clips can be found on mathgotserved.com under AP Calc. Thanks again for watching and have a wonderful day.